Problem solvers. We're towards the end here, one of the last three lessons. We're doing primes and divisibility. This is going to lead into the next lesson on congruence. So if we have two integers and a over b is an integer, we say that b divides a, or equivalently that b is a factor of a. This notation gets really annoying. Look at these lines very carefully. B divides a, we use a straight vertical line, and that's not a fraction. That doesn't mean b over a. It means that a over b is the integer. So a over b is the actual fraction we make, but b going into a, we put b first, and then slash for divide. So b goes into a, b divides a. Another way to say it is that there's an integer, so that a equals b times m. We're most often going to use this version. So when you get that integer is m. We're going to use this a equals bm because you get an equation that you can play with. So that's the most common, that third one is the most common way to play with the definition. Natural number greater than 1, so not 1 itself, is prime if it has no natural divisors other than 1 and itself. Any number that's not prime is called composite. There's the first list of primes. I don't think you really need to memorize primes, but maybe under 100 is good, but don't memorize, thousands of primes. One proof that is heterogeneous is that there are infinitely many primes. They don't ever run out. Fundamental theorem of arithmetic means if you have any number that's composite, or if it's prime, I guess, it can be completely factored into prime numbers and powers of those prime numbers, other than rearranging the terms. So you probably did factor trees like this as a kid. If it's a prime, then the factor tree is very boring. The greatest common divisor of two non-zero integers is the largest integer that divides both numbers. The Composite there is, I think there was a typo inside somewhere. If the GCD of two numbers is 1, then we say that the numbers are relatively prime. So not prime themselves, but if you think of like 4 and 9, those numbers are relatively prime because they have no factors in common, even though they're both composite. Least common multiple goes above the numbers, the smallest positive integer that's a multiple of both. So you go above them, but you go to the first thing, the smallest number that's a multiple of both. And then there's this fact about LCM and GCD. If you put it on the other side, the LCM and the GCD multiply to the original, to the product of the original two numbers. So here's some practice. Find the GCD and the LCM of the following two numbers. You should get out some pencil and paper and try that. I'm not going to do it in front of you. The division algorithm is a method for kind of doing long division to figure out the GCD. In this PowerPoint, I'm not going to go through this super carefully, but I really, really encourage you to go to the ICE sheet because I think, if I remember right, what I did is I did one out, maybe even a couple, 3 or 4 with integers, and then I did it with polynomials. And so to see this carefully, I would really encourage you to go look at the ICE sheet. But what you end up with by the time you're done is you end up with the quotient, the divisor, the dividend is the original thing you're trying to divide, and then R is the remainder. And so some problems will try to use this kind of as the end game already. I think you guys already saw that some with polynomials. Speaking of that, I might have done those on the polynomial ICE sheet instead of this one, but they're both there on YouTube. Okay, GCD is always a linear combination, so another way to write it is the small positive integer where you have this. So D is the GCD, A and B are the two spots, and then P and Q are integers that make this work. It's trying to find P and Q is generally pretty hard, but really what the advantage of this definition, this is a strange definition for GCD, is it gives you an equation to play with. If you can prove that P and Q are integers and you can create AP plus BQ equals 1, that tells you that A and B are relatively prime because the D is the smallest positive integer. But again, this is just a way to play with. Here's an example of the Euclidean algorithm. The way to think about it is start with the dividend, and what you're always going to do is you're going to bring the divisor, after one round of it, you're going to bring the divisor to the down and to the left. You're going to bring the remainder down and to the left. You're going to ignore the quotient, and then do it again. Bring those two numbers down. Do it again until you get a remainder of 0. The last divisor that you get, that's the GCD. Same thing on the crazy one. Euclid's lemma is for the elements. Modern notation: if you divide a product with a prime divides a product, then it has to divide one of the two things in the product, because a prime number can't be split across two factors.